Okay, so where we were, yeah, here. So you see the recursive calls resulting too many branches, like 3 branches for the first child node, 2 branches here, 1 branch here. So when n increases to a larger number, this tree, the total number of nodes in this recursive call also increases. So it's actually an exponential increase. Okay, so if we let T of n to denote the total number of recursive calls, okay, made to this procedure. Okay, so it's actually that many. T of 4 at the root node, 4 recursive calls here, 3 recursive call here, 2, 1, 0, right? And we can simply write the recurrence like this. The recurrence equation would be T of 4 equals 1 plus that many. Okay, so a recursion like this actually is something that increases insanely fast. Okay, it's just the results, the mathematical results of solving these recurrence is that actually it's an exponential function. It's the 2 to the power of n, which is much faster, way faster than what we can expect from an efficient algorithm. Okay, so that also explains that whenever we increase the number by 1, it actually almost doubles the running time for solving the same problem. Okay, so this is also not surprising because the design of our algorithm doesn't consider, doesn't save the results from previously solved problems, right? It's not considered at all. So we basically, what we want to do is to, like, whenever we solve something, we put it into some records, put it into some table, and later on, each time when we solve it, before we solve a problem, we will need to look up that table to check whether it's there or not. If it's already there, we just return it. Okay. So this another thing of this exponential is that because another meaning of this exponential function is that the cut rod considers all that many possible ways of cutting, right? And from the tree graph, from the tree plots, these 2 of n to the power of 2 to the power of n minus 1 is also the number of leaves in the recurrent tree, or the number of paths from the root to the leaves. Okay. All right. So it's time to consider some dynamic programming solutions. Okay. So we find that a naive solution doesn't work. So we want to save the subproblem only once. And after it's solved, we will save the solution. Okay. And later, if we need to refer to this subproblem solution again, we just look it up rather than recomputing it. There's a difference here. To look it up, we don't, if we want to look up some solution, we don't apply recursive calls. But if it's a recomputation, then it's a lot of computation. It's a lot of recursive calls. Okay, so it's actually a time and memory trade-off. We need to use some additional memory space. And actually, we will look at 2 different approaches for rod cutting problem, 2 different of dynamic programming approaches. And I think today we will have time for the first one, which is a top-down dynamic programming. So it's called top-down with memorization. So it's a little bit similar to a recursive, a natural or naive recursive procedure. Okay, but we need to rewrite it so that we will save the results for each subproblem in an array. Okay, so in this time, it could be an array or hash table, but in this time, we write it into an array. And now we need first checks whether it has previously solved the problem or not. If yes, we will return the saved value from the array. If not, we will compute the value in the usual manner, which is the recursive manner. Okay, and this procedure is memorized. Okay, this is the term that we use. Okay, let's see this memorized or cut rod procedure. Okay, so it also takes the price table P and the input number N, the integer as inputs. All right, so it initializes a auxiliary array, which is R from 0 to N. Okay, so these R from 0 to N will be used to save the results to those subproblems, to all the possible subproblems. Okay, and this for loop will simply initialize everything to negative infinity. So this is an unknown value, and as we have seen before, this negative infinity is smaller when it's compared to any numbers. So it's basically for the convenience of for the convenience of future comparisons. And we also need to rely on the helper function, which is memorized cut rod auxiliary function, which is actually the function that does the heavy lift for us. Okay, and this auxiliary function takes additional inputs, which is the R, which is the new array initialized here as the third argument. So we have P and R, N and R, 3 arguments. Okay, and what really does the computation is within this procedure. Okay, so this memorized cut rod aux procedure, it's a memorized version of the recursive cut rod. So you see, now at the beginning of this procedure, it will immediately check, right, whether some values is already known. Okay, if the nth value of the R array is greater than 0, then it means it is no longer unknown. Okay, so only the negative infinity indicates unknown. So if it's greater than 0, if it's a positive number, then it's already the result. We will simply return it. Okay, so that is a necessary step when we write a top-down dynamic programming algorithm. We need to check whether the results exist. Okay, so if not, then we will proceed on to the next lines of code. Okay, so the line 3 to 7, right? It's actually computes the desired value, which is R of n, in the usual manner. Okay, so for example, when the smallest case, right, when the input is 0, doesn't make sense, right? We will just let Q to be 0, and we will mark that R of n to be Q, which is 0, and we directly return Q, right? And if it's a larger problem, then we will set the candidate to be in negative infinity, and this will be the basis of our comparison. And then we will iterate over all possible places of cuts, which is exactly what we did before, right? We will iterate from 1 to n, which are all possible places to cut. Hello, everyone. Oops, it's my recording. And then the Q will be compared. The Q will be compared to all possible places, all possible combinations. Okay, which is to directly sell the first cuts and the further optimization on the right parts, which is the recursive call of the function itself. Okay, the recursive call will further optimize the right half, which is of length n minus I. Okay, so the Q will be used to memorize, will be used to store the results of the maximum elements or the maximum choice among all these possible, all these 1 to n possible ways to cut the rod. Okay, and after Q is returned, it will be stored. So this line 8 is also a critical step, because if we don't store Q to Rn, then the Rn will the R will not be updated, and all the elements in R will still be negative infinity, right? And then that doesn't make sense. It doesn't help us at all, right? In order to make sure the external space will help us to memorize space, we need to store the results to the memory space, to the array, whenever we get a solution. Okay, so this is the difference from the previous simple recursive solution. I think the two major differences here. The first part to check whether results exist, and the second part, which is to save the results, save the solution once we have got some solution. All right, so let's look at an example. Okay, I think it will help us better understand the algorithm. We'll start from a very simple one, which is n equals 2. All right, and a table like this. This is the, I think it's the same table that we shown before. Okay, the code is here. So I didn't show the other function, right? The other procedure is to initialize the table R. So after the R is initialized, we will have something like this with R negative infinities in the elements. And then the first call is on n equals 2 here, right? Because that is our target, okay? That is our goal. We will call n equals 2. So the result would be the Q will be initialized to negative infinity because n is greater than 0, right? So the if will not be executed. Only the else will be executed. The Q will be negative infinity. And then we'll go into the for loop, right? The first iteration of the for loop, the loop counter is 1, right? And we basically need to compare the Q, which is the negative infinity, with P1 plus the recursive call on 1, right? Because 1 is n minus I, and because I is 1, so it will be 1 here, right? So that's the first iteration of the for loop. So now let's step into this recursive call. Okay, so this recursive call will result in another Q, right? Because the n is greater than 1, right? So a new Q, but this Q is within the scope of this recursive call, but it's different from this black Q. Okay, so this blue Q will be the results of comparing negative infinity with P1 plus memorize cut rod on 0, right? Because within this recursive call, n is 1, so n minus 1 will be 0, right? And now we have a second recursive call. The second recursive call would, let's just go further into it, right? So now because the input is 0, that means our the if parts of our code. Okay, so the if part of our code now will be executed, right? So the Q will be initialized to 0 now, and it will be saved to R0, right? According to the line 8, the Q0 that has 0 value will be saved to R0 because the 0 is the input here. Okay, and the Q will be returned. Okay, and the Q will be returned to the upper level. So after it's returned, the comparison for the blue Q will be the comparison between negative infinity and 1 plus 0. And this 0 is just the 0 returned by the Q. Okay, so the blue Q would be 1. And after the 1 is computed, it will be saved to R1, right? Because for the blue Q, the corresponding input is 1. R1 will be saving this blue Q. And the blue Q is also returned to the, will be returned to the upper level again. Now we are going to compute the black Q, right? So the black Q would be the comparison between the negative infinity and 2, which is 1 plus 1, the blue Q, which will result in Q. Okay, so the black Q will be 2, which means that it's the current value for the black Q. Okay, so the black Q will be changed from this negative infinity to this 2. All right, so we're not done with the black Q yet because there will be a second iteration, right? After the iteration for I equals 1 is done, we'll go into the second iteration, which is I equals 2. And I equals 2 means that, okay, so we now need to compare the maximum among the existing value, the existing value for black Q, right? The current value for black Q, and the option of selling the left part, which is length 2, and the recursive call on the remaining part, which is of length n. Okay, so this green part is a recursive call, but since now we have this first 2 lines of code in the function, it will directly check whether the R0 is greater than 0. So it's actually already greater than, it's already solved before. So we will directly return R0. Okay, so this is where the dynamic programming occurs. We don't need to solve it again. We just return the value, and it will be directly return the value 0, and we will compare 2 and 5, which will result in a new value for the black Q. Okay, so this black Q will be saved to R2, and now we are done with the algorithm. Okay, so all the values in this R table is saved. Okay, so that is how we return the results of Q equals 5, which is the maximum revenue for the input length of 2. So if we observe how we update the R table R, it's basically updating the smaller problems first, right? We solve the smallest problem first, and then solve the greater one, and we solve the last one, which is the one we need. And which also means that the solution to the original problem depends on the smaller subproblems. In order to know R2, we need to know R1. In order to know R1, we need to know R0. Okay. All right. So that is a complete example of a top-down dynamic programming approach for the rod cutting problem using a small input n equals 2. So I think you can, after the class is over, you can work on it on your paper by reading these slides for several times. You can also watch the video. So after you have figured out the difference between these Qs at different levels, it'll be much easier to have the whole picture connected. Okay. So yeah, I think that's so much for the dynamic programming today. And next week, we're gonna continue this topic with more examples and a different way of dynamic programming approach for rod cutting. All right, any questions so far? All right, so good. If there's no questions, I'm gonna stop the recording right now.